This guy was fascinating, a lot of different aspects to his life. And as I'll explain to you, I think one of the things that I got out of digging into his background and history was the fact that, and this is purely my own idea, I didn't see this written up anywhere. I think that he was obsessed with neutrons. And I will go into the reasons for that as we go through it. But he spent a good portion of his professional career worrying about neutrons. It started really with the discovery of the neutron in 1932. I'm going to talk more about that. Chadwick discovered the neutron. And he wrote a paper about 7 years after the discovery that pretty well laid out the science of neutron stars, as well as white dwarfs and black holes, which are all related, as I'm going to show you. And then, of course, he took on the Manhattan Project, and one of the main focuses of the Manhattan Project was the generation and control of neutrons, which were necessary to provide a chain reaction, an explosion, basically. So he was, I think, obsessed with neutrons, and so I added this sentence at the end here. I stole the rest of it from the internet, but that's my words. He was obsessed with neutrons.
Yeah, footnote.
Pardon?
Footnote.
Yeah, I need a footnote. Okay, so we'll talk more about that, but as we go through it, we'll talk a little bit about the discovery of the neutron, the papers that he wrote about neutron stars and other things, the progression that I'll outline in some detail for you. As a star explodes in a supernova, progresses to a white dwarf, neutron star, and sometimes to a black hole. And it turns out that it all depends on the mass of the supernova. So if it's got a very small amount of mass, it may stop at a white dwarf. If it's got a little bit more mass, it may go to a neutron star. And if it's really huge in terms of mass, it will become a black hole. So this is kind of the progression. Talk a little bit about the Manhattan Project. I already spent a good deal of time on that, and a little bit about the hydrogen bomb, and then summarize. He was a real genius, and one of the things that I didn't put on a slide that impressed me was that he was so smart as a kid that he skipped from the 2nd grade to the 5th grade. He skipped 3rd and 4th grade. They were so impressed with his ability. Of course, what that did to him socially, anybody can guess. But turned out he was a very good manager. And as happened to Einstein and many other scientists, Allard, toward the end of his life, toward the end of his career, really, he became a pacifist. And that led to his professional disgrace in a way. He lost his security clearance. And we'll talk a little bit about that. But he was really the father of the atomic bomb. And that's how he's been characterized in a lot of the writings that I've read about him. So he was born in 1904. His parents were prosperous textile importers in New York City. At the age of 21, he graduated from Harvard with a degree in chemistry, an undergraduate degree. And 2 years later, and remember we talked about Göttingen, he got his doctorate from Göttingen, which, you know, at that time was the premier university in Europe for scientific and technological subjects. In the same year, he co-authored a paper with Max Born, a famous scientist that I haven't spoken about yet, on the separation of motions of nuclei and electrons in a molecule. So he felt that that you couldn't characterize the motion of a molecule simply as the motion of a molecule. There was the motion of the nucleus, and that was different from the motion of the electrons. And 2 years later, after getting his doctorate, he became an associate professor at Caltech. So he went up very fast. Usually you start out as an instructor, assistant professor, then if you get tenure, you know, maybe in 7 years, you become an associate professor. But they recognized his genius early enough so that he was promoted almost immediately. In 1930, he wrote a paper predicting the existence of the positron, which wasn't discovered until 6 years later. So he was very good at predicting things. In 36, he became a full professor at Berkeley. And in 39, he co-authored important papers on neutron stars and black holes, neither of which had really been discovered at that time. So he predicted a lot of things, and he was right, just as he predicted the atomic bomb, and he was right. He married in 1940, and in 1943, he was involved in the Manhattan Project. He started turning in people that he didn't trust. It was ironic because eventually he himself was subject to the same level of scrutiny. In 1944, he organized Los Alamos Laboratory to focus on implosion. The problem was that if you implode the uranium too quickly, okay, then you might get a premature explosion. It wouldn't be the full effect. But if you do it too slowly, then you might get a series of smaller explosions, because now the neutrons are like floating around. So they had to find a way to implode the uranium very, very quickly and very evenly. And they had to contain the neutrons with tamping material around the explosion. So he was very much, as I said, concerned about these neutrons that were floating around. And that was one of the biggest problems that they had at Los Alamos. And other scientists developed ways of having a perfectly uniform implosion by putting explosive devices around a sphere. In 1945, after the dropping of the atomic bomb, he left Los Alamos. He no longer was interested in teaching. And in 1947, the Atomic Energy Commission came into being, and he was appointed as the chairman of its General Advisory Committee. In 1954,
Alan, excuse me, was that Caltech or University of California?
Caltech is Berkeley, isn't it?
No,
Oh, I'm confused. It's Berkeley. It's Berkeley. Yeah. Berkeley. I was only in California for a short period of time. So. All right. Oppenheimer had his security clearance taken away by Eisenhower in 1954 because he resisted going into the development of the hydrogen bomb. Had a big fight with Teller. We'll talk a little bit more about that. In fact, Teller testified against him because some people think because of a personal grudge, because he effectively forced Teller out of the development of the A-bomb. All Teller wanted to do was develop the H-bomb. And eventually that's what he did, but they had quite a few confrontations. So Oppenheimer's research into fission and physics pretty much stopped after his security clearance was pulled. He went on to develop the World Academy of Arts and Sciences in 1960. He continued to lecture and write on physics. And he died, ironically, in 1967, which was the same year in which the neutron stars were first observed. But they were first found after his death. If he had lived a few months longer, it is speculated that he would have won the Nobel Prize. The results of the hearing, McCarthy hearings on Oppenheimer in 1954, provoked a lot of outrage in the scientific community. In England, von Braun said, in England, Oppenheimer would have been knighted. Einstein quipped that AEC, Atomic Energy Commission, should stand for Atomic Extermination Conspiracy. David Lilienthal wrote in his diary, it is sad beyond word about Oppenheimer's loss of his security clearance. It is sad beyond words. They are so wrong, so terribly wrong, not only about Robert, but in their concept of what is required of wise public servants. And Edward Teller was shunned by a great part of the scientific community because of his testimony against Oppenheimer. As I said, Teller's plans for a hydrogen bomb were opposed strongly by Oppenheimer. So let's talk, go back in history now a little bit about the discovery of the neutron. It starts in 1920. Rutherford, who of course is most well known for discovering the nucleus of the atom. Remember, he shot charged particles at a gold foil, and most of them either went straight through or were deflected slightly, but every once in a while one came straight back. He said famously, it's like firing a cannon at a piece of tissue paper and having the cannonball come straight back at you. So he knew that there was some very strong source of repulsion for these positively charged ions, and determined that, and from his research determined the size of the nucleus by measuring the number of, the percentage of particles that came back at different angles. So he was able to determine the size of the nucleus, the existence and the size of the nucleus. So he said that in 1920 that an electron and proton could actually combine to form a new neutral particle. There's no real evidence for this, and it was left to Chadwick, where some research in Germany by Bode and Becker had found that there was radiation emitted by the beryllium, and some people thought it consisted of high energy photons, but Chadwick noticed some odd features of this. began to think it might instead consist of neutral particles, such as those Rutherford had proposed. One experiment in particular caught his attention. The Curies had studied radiation from beryllium as it hit a paraffin wax target and found that it knocked loose protons from hydrogen atoms in that target. And those protons recoil with very high velocity. So the feeling was that photons could not do that. There was something else involved. Photons, of course, have no effective mass and could knock particles as heavy as protons loose from the target. So in 1932, he became convinced that the radiation that was ejected by the beryllium was in fact a neutral particle about the mass of a proton. Turns out that the mass of a neutron is slightly more than the mass of a proton. He tried other targets and determined the mass of the new particle was what I just said, slightly more than the mass of a proton. Chadwick also noted that because the neutrons had no charge, they penetrated much further into a target than protons would. So this discovery and this effect of neutron, or capability of neutrons, became very, very important because it can be used to destabilize nuclei and, in fact, make them radioactive. In February 32, he published a paper about the possible existence of a neutron. A few months later, he published a more detailed paper confirming the existence of a neutron. And by 1934, it was found that the neutron was a new fundamental particle. And this changed scientists' view of the atom. They already knew that the atomic weight and the atomic number of atoms were not the same, that there was additional weight over and above the number of protons. Chadwick got the Nobel Prize in 1935 for this discovery. And it was soon realized, of course, that neutrons could be used to penetrate nuclei because they didn't get repulsed by the nucleus because they had no charge. And what repels protons or electrons from a nucleus, well, protons, is the strong positive charge of the nucleus. So like charges repel. Protons, in order to get a proton into a nucleus, is very, very difficult. The repulsive force of the protons already in the nucleus is very strong. It's that same repulsive force that prevents gravity from pulling me through the floor of this room. It's the electrical repulsion that keeps me from going through the floor. Soon scientists found that hitting uranium with neutrons resulted in the fission of the uranium nucleus, splitting of the atom, and release of incredible amounts of energy. Chadwick did work on the Manhattan Project. He was brought into it by Oppenheimer.
What is a neutron?
I'm sorry?
What is a neutron?
It's a particle with no charge.
A particle with no charge.
Yes. A proton, of course, has a positive charge.
Right.
An electron has a negative charge. A neutron, as its name implies, is neutral. Has no charge.
Why should there be a neutron?
Why what?
Why should there be a neutron?
If I could answer that, I'd be on the next plane to Oslo.
Doesn't make any sense, does it?
Well,
It's a Sikorsky effect.
Yeah. In the 1930s, we talk now about neutron stars, astronomers began to ponder the future of a star when the nuclear fuel in the star burns out. When the energy generation within a star falters, gravity begins to take over, and it compresses the mass of the star. Our own sun will end up as a white dwarf, and eventually, maybe even that will burn out and become a brown dwarf or a red dwarf, a much cooler star without being able to produce any further energy. The core of a white dwarf is a dense mix of nuclei and a sea of electrons, but the fates of larger stars than the sun were less clear. Something called the Tolman-Oppenheimer-Volkoff limit is an upper bound to the mass of cold, non-rotating neutron stars, analogous to the Chandrasekhar limit for white dwarf stars.
What is a neutron star? Why neutron?
I'm sorry?
Why is it called a neutron star?
We'll get into that in a moment, yeah, okay? But basically, most of its mass now is of neutrons, okay? Made up of neutrons. The first gravitational wave event was due to merging neutron stars, which are thought to have collapsed into a black hole within a few seconds after merging. And the limit, therefore, they think is close to about 2.17 solar masses. In the case of a rigidly spinning neutron star, the mass limit is thought to increase by up to 18 to 20%. Okay, so it can be a little bit more massive and still be a neutron star. Researchers understood that a white dwarf with too much mass is unstable, and its own immense gravity should compress it into something denser, possibly something made entirely of neutrons. So in a paper that was published early in 1939, Oppenheimer and Volkoff, both at Berkeley, proved that neutron cores, like white dwarfs, could not be indefinitely heavy. But they could find no stable solution to their equations if the neutron core had more than about 70% of the sun's mass. Astronomers, astrophysicists now know that such large cores result from the deaths of stars several times as massive as the sun. For a larger core, collapse must proceed further, but into what? So Oppenheimer and Snyder answered that question in a paper later in 1939. Since static solutions to their equations seemed to be impossible, they looked for solutions where the structure of the object never stopped changing in time, representing continued contraction. So again, the importance of mass is something I cannot stress too much. If the mass of a star, say like our sun or even smaller, is not sufficient so that the gravity cannot overcome the pressure of gas and other pressures that we'll talk about that develop over time, then the star cannot collapse into a white dwarf, collapse further into a neutron star, or collapse even further than that into a black hole. The more massive the star is, the further the collapse will go. So for stars that are only slightly more massive, say about 2.17 times as massive as the, less than 2.17 times as massive, but more massive than the sun, they can become white dwarfs. more than 2.17 times as massive, they can become neutron stars. And then much more massive than that, I think about 5 times more massive, they can become black holes. So it all depends on that initial mass of the star that we're dealing with. So they predicted that under extreme conditions, they predicted that something could come about of what we now call a black hole.
I mean, a star can become a black hole.
Absolutely. That's where they come from, we think. That's what happens. As the gravitational pressure, because of the extremely large mass, continues to compress the star, eventually it gets to the point where the gravitational effect is so great that light cannot escape from the star. As Einstein's theory and Eddington's experiment showed, gravitational fields can bend light. Okay? So if the star has sufficient mass, the escape velocity, which depends on the mass, is so great that even at the speed of light, the light cannot escape. It just gets bent around and brought back in. So we never see any light reflected or originated from the black hole. Because any light that approaches it will be captured. Any light that tries to escape will simply be rerouted back in. So it appears as what we call a black hole, a dark place in the sky.
In one of your previous lectures, didn't you mention some Frenchman who predicted a black hole also?
I'm not sure.
I thought someone predicted a black hole.
Well, Schwarzschild in about 1916 or 17 solved Einstein's gravitational equations and came up with a singularity, which is akin to a black hole.
I mean, the point is, this guy just used Einstein's equation. He didn't really have the neutron theory. He just said
Right.
it got so big, you'd end up with a black hole. So
Right.
I thought it was predicted back then.
Well, yeah, 1960. Yeah.
But he was a German though.
Yeah, this is some French. This is a French. Wasn't this a French priest that?
The Mater, yeah.
But he did the Big Bang, right?
Yeah, he was the Big Bang guy. Right? Yeah. I'll have to look at some of the previous lectures. John Wheeler of Princeton noticed, well, the paper was hardly noticed until the 1960s. And then astrophysicists began to consider that such extreme object might exist. And John Wheeler of Princeton University came up with the name black hole, for what is now a standard element of astrophysics.
First time that name was used,
Yeah,
black hole.
yeah, 1960. The matter in an extreme collapsing object, according to Oppenheimer and Snyder, would retreat inexorably inward. Any escaping radiation would suffer an increasing gravitational redshift. So we have to talk about that, because it turns out that gravitational fields have an effect on time, they have an effect on wavelength, okay? And a red shift means simply that the spectrum of whatever the object is shifted toward the longer wavelengths. Hubble, of course, found that galaxies that are further away are moving away faster by measuring their red shift. The greater the red shift, the greater the speed at which the galaxy is moving away from us, or a star even, or a planet. So if we look at the sun, for example, one side of the sun rotates about once every 30 days. It rotates. So one side of the sun is always approaching us, the other side is always moving away from us. So we are, because the sun is relatively close, we're able to actually measure the redshift of the part that's moving away from us, and the blue shift, the shift toward a higher frequency, shorter wavelength of the part that's moving toward us. So we can actually measure the speed of rotation of the sun. So if we looked at collapsing objects, they become redder and fainter because some of the radiation shifts out of the visible spectrum. It goes infrared, in other words. It goes below the red end of the spectrum. And so we don't see as much light coming from that object. So as the authors Oppenheimer and Snyder said, the star tends to close itself off from any communication with a distant observer. Only its gravitational field persists. So this tremendous mass has tremendously strong gravitational attraction. And as it gets compressed, the gravitational force on the surface becomes even stronger. Because, as I've pointed out before, gravity depends on what we call an inverse square law. If you reduce the size of an object to 1/2 of its former size, gravity is going to increase as 1/2 squared. Or it's going to be 4 times, it's going to increase as 2 squared. It's going to become 4 times greater than it was for the original object. And so as it begins to compress, gravity begins to increase, and it compresses further, and it increases even more until something else intervenes. And we're going to talk about what that something else is. But the only thing that can resist it initially for a normal sized star is the pressure of the gas that's being exploded, in effect, due to fusion within the star. And that pressure is not as great. Furthermore, what happens when you reduce the radius? When you reduce the radius, you reduce the surface area. Okay? So that changes the pressure as well. So now we have an object that begins to collapse. Gravity is increasing rapidly, okay? And the pressure cannot keep up with it. Furthermore, the star begins to run out of fuel, so pressure is even further reduced.
The temperature goes up also.
Temperature goes up, right? So there is some increased pressure because of that. Nevertheless, that pressure cannot keep up with this inexorable gravity that's pulling the star tighter and tighter, compressing it more and more.
The mass has not changed.
The mass has not changed, no. But because the mass is more concentrated, gravity on the surface is stronger. Okay? And it's this inexorable force compressing the star up to a point. And we'll talk about what happens to some stars as you reach further states of compression. According to the author Tucholsky of Cornell, Stuart, you ever met him?
Sorry?
Did you ever meet Tucholsky?
No, I not really.
Yeah. He says that it fascinates me why that paper was neglected for so long. And Tucholsky and Shapiro wrote this book, Black Holes, White Dwarfs, and Neutron Stars, which I have read, is really worthwhile. A lot of science. There was an instinctual revulsion against unlimited collapse. And a Russian scientist suggested that you had to modify quantum mechanics to make sure it couldn't happen. The Oppenheimer-Snyder paper goes against the prevailing thought of the time. He says it really stands out. So like many of Einstein's works, it was not something that was easily accepted. The idea of unlimited collapse. So gravitational attraction is the only force acting to compress a star, okay? In the initial stages of compression, gas pressure is the sole resistive force, okay? So as the star begins to collapse, running out of fuel, okay, the pressure of gases exploding within the star due to fusion is reduced, okay? And gravity begins to take over. However, you get to a certain point where the electrons in the atoms inside the star are so tightly compressed that they can no longer come together. Okay? It's called degeneracy. So if the electron degeneracy pressure, because you can't force electrons into the same orbits, right? They're in different orbits. Or orbitals, we should say.
According to quantum mechanics.
Yeah. So you can't get them any closer. They begin to provide an additional resistive force against gravity. Okay? For stars without enough mass, that resistive force may be enough to stop the compression. Okay? There's not enough mass, gravity is not strong enough to overcome that resistance. So the compression stops, and what you have is a white dwarf star. Okay? If the compression is strong enough, if there's enough mass so that gravity is very strong, that resistive force can be overcome by gravity. And if it is, compression may continue until all you're left with are neutrons. You have stripped away all the atoms, and all that's left are neutrons. And the neutron degeneracy can sometimes stop that compression. And if it does, then you're left with a neutron star. A star that consists primarily in its core of neutrons.
Where did the electrons?
The electrons and protons presumably form the neutrons. Okay? Now, if the neutrons pressure, if the degeneracy of neutrons is not strong enough, if there's so much mass that gravity can still overcome that force, then compression continues indefinitely, and you end up with a black hole. So they're all related in this way. Can you visualize this? And can you see the importance of mass in determining what kind of object you end up with? Yes, sir.
Going back to the white dwarf, so you have atoms. What kind of atoms are they? What element are
Helium, probably, mostly helium.
Whatever else, whatever it.
Yeah, it can be carbon. It can be some carbon atoms. Yeah, but you're still having some fusion. In other words, a white dwarf does produce some light. It's releasing energy. Okay. Whereas a neutron star, then fusion is basically stopped. Okay.
I understand these white dwarfs are about the size of the Earth, is it?
Oh, yeah, I have a slide, yeah, yeah.
What exactly is electron degeneracy or neutron degeneracy? They say that causes a pressure, but what exactly is the electron degeneracy?
Well, it simply means that you can't force two electrons into the same space, the same orbital,
Well, the same
with the
quantum-
same spin and so forth.
The same quantum state.
Same quantum numbers, right?
Yeah.
Well, the quantum state.
Quantum
You
state.
You can only fit two electrons in one quantum state, up and down.
Right,
That's Pauli found that.
right, the Pauli exclusion
Yeah, but-
principle.
So I think what happens is eventually the electron is forced to join the proton, so it becomes a neutron.
Yeah,
And then all the other electrons, well, there should be a perfect match because there's all,
Right.
each electron has a
same
proton.
number,
So,
same number, yeah.
And neutron
But each
degeneracy
proton
is the
has
same
several
idea as electron degeneracy. You can only fit so many neutrons into a quantum state. After that,
then
they
it
won't
becomes,
go.
it becomes a quirk problem and
Well, that's
less,
something else, yeah.
we're not sure, but essentially it's the same problem, same kind of problem, quirk degeneracy.
Yeah. So,
Is there any reason that the protons are stripped off and the neutrons stay if they have about the same mass?
when you say stripped off,
No, you're saying the protons and electrons
form the neutrons, yeah.
So there are no protons in a neutron star.
Not in the core, not in the core. There may be a sea of protons and electrons in the upper atmosphere. Yeah, yeah. Does that answer your question?
Yeah, and he's an answer later.
Oh, okay. Thank you, Stuart.
What is a neutron?
Okay.
I think your answer was right, though.
So again, I emphasize that the fate of a star depends strongly on mass. If the initial mass is less than about 1% of the sun, okay, all these are in comparison to the sun, then you got a planet. Take Jupiter, for example. Jupiter would have to be about 800 times larger to have become a star, okay, a small one at that. But as we look around the sky, we see that many, many star systems are binary, some are even tertiary systems, okay? For instance, Sirius is Sirius A and Sirius B. There's two stars. So you're not looking at one star when you look at Sirius. If the mass is between 1% and 8% of the sun, you get something that is called a brown dwarf. In other words, very, very little energy is being produced. It's too small. So the pressures inside the star, again due to gravity, cannot raise the temperature enough so that the speeds of the particles inside the star are not great enough to produce a lot of fusion. Okay? Fusion being the combination of two hydrogen atoms to form helium eventually. Okay? Or other combinations. But it depends on speed, and speed depends on temperature. Temperature is simply a measure of the speed of molecules or particles. Okay? And you can view that as simply the number of collisions per unit time. So the faster the particle moves, the more collisions there are going to be. The more collisions per unit time, the higher the temperature because the greater the friction, which occurs because of collisions. If we go from 8 to 25%, you can get a helium white dwarf, okay? A star that consists mostly of helium and is producing some energy, but is very small. As the initial mass goes up, gravity goes up, pressure goes up due to gravity, and temperature goes up, and so you get more fusion. So you start to produce higher level elements, carbon and oxygen. And you get a carbon-oxygen white dwarf. Between 8 to 12 times the mass of the sun, neon and magnesium come in, higher level elements. Between 12 and 40 times the mass of the sun, you can get a supernova that will produce a neutron star. So now you move beyond the white dwarf stage, okay? Now you've got enough pressure so the electron degeneracy can be overcome and you get a neutron star. If it's more than 40 times the mass of the sun, the neutron degeneracy cannot stop the gravitational collapse, and you get a black hole. That make sense?
What is the composition of a black hole? Do we know?
Nope.
It ain't telling.
Question? Yes.
Neutron degeneracy, they have no charge, so I don't understand what pressure is happening there. You said the electron, they have the common charge.
Well,
The neutrons
charge,
are neutral, what
charge
is the element?
is more involved with the quantum state. In other words, spin. There's 4 different quantum numbers, and you can't have 2 neutrons with the same quantum numbers forced together. Okay, they can't occupy the same space.
Okay.
So that's where the pressure comes from, because you're so compressing the neutrons that you're trying to force them to occupy the same space, and they resist that.
Gotcha.
So that's where the pressure comes from. It's called the Pauli exclusion principle, Pauli. There's a question over here, and then I'll come back there. Yeah.
Paul, I was thinking about red dwarf stars. I assume in their final evolutionary state, they'll be, from your chart here, either a brown dwarf or a helium white dwarf.
Yeah, in between, you can get red dwarfs.
No, I don't think red dwarfs do that. I think they just sort of, they last a long time. I mean, and most of the stars in the universe are really red dwarfs. And they never go into, they just exist for a long time.
Yeah. And
Millions of
that's
years.
what we think the sun will eventually become.
No, it's gonna become a red giant. I mean, I think it's.
Well, first it'll become a giant, then it'll shrink. Yeah.
Can we detect a black hole?
I'm sorry?
Can we detect a black hole
Yes.
Yes, we have, but by gravitational waves.
by gravitation?
No, we've seen them in the centers of galaxies.
Yeah, if you look around the sky, you know, you can see areas where there's no stars.
But you can also detect,
And things orbiting it fast.
right, the things are orbiting,
Right.
so you know they're massive.
Right.
There's
Isn't
certain,
that where it's supposed to be in Bermuda Triangle? Is that what Black Star
No.
usually is?
No,
Triangles are different, totally different
No,
ball.
just saying. Where's it located?
so this shows you a little bit more about the relationship between white dwarfs, neutron stars, and black holes. In a white dwarf, electrons run out of room to move around and prevent further collapse, and protons and neutrons are still free to move around. If the mass of the star is less than about 1.4 solar masses. If it's between 1.4 and 3 solar masses, gravity can overcome electron degeneracy, and neutrons can be formed from electrons and protons. And at 3 solar masses, neutrons run out of room to move around. And if it's less than that, neutrons can prevent further collapse.
Yeah.
Above 3 solar masses, you get gravity wins, and nothing prevents further collapse into a black hole.
Why did it say 40 on the previous slide?
Different authors.
well, it's thought that at the center of a galaxy, like our galaxy, the black hole has a mass of 1 million suns or more.
Yeah.
Very big.
And growing probably, right?
Who's counts?
Never had this space.
Yeah.
What about the idea that there is a black hole at the center of every galaxy?
Yeah, well, we think that's true. So here, so white dwarfs about the size of the Earth, about equal to the mass of the sun. Neutron stars, we think, are about 6 miles in radius and about 1.4 times the mass of the sun. 1 teaspoon of neutron star material would weigh about 100 million tons. 1 teaspoon. So think of something that is so extremely dense that a very small amount of it would weigh a tremendous amount. So here again it says 3 times the mass of the sun, you'll get a black hole. If we had these densities, you could cram all of humanity into a volume the size of a sugar cube. Naturally, the people thus crammed wouldn't survive, neither does the matter that forms a neutron star. This matter, which starts out in the original star as a normal, well-adjusted combination of electrons, protons, and neutrons, finds its peace, also known as a lower energy state, as almost all neutrons in the neutron star. So this is a picture of a neutron star superimposed on a map of Chicago. Notice the spin rate of this star with a radius of 6 miles, a mass 1.4 times greater than the sun. It spins at 38,000 revolutions per minute. It is really spinning very, very rapidly. It has a density of about, let's see, that would be 100 trillion grams per cc. And a magnetic field of about a billion, 10 to the 12th is a billion, right? A billion gauss. So a very strong magnetic field.
No, that's a trillion.
I'm sorry, a trillion?
10 to 12.
Oh, right. 10 to the 6th a million, 10 to the 9th a billion, 10 to the 12th a trillion. A trillion gauss. Okay? Extremely strong magnetic field. And that magnetic field, remember this thing is spinning very rapidly. It is sweeping across the space around this neutron star,
It's not as big as our national debt.
creating a lot of radiation. And something called a pulsar, we think, is a neutron star that may be spinning very, very rapidly.
Now the surface must be close to the speed of light. The outer surface of that spinning star must be going at about half the speed of light.
Okay.
That must-
Relative to what?
Well, to whatever you're measuring the spin in.
These stars, these neutron stars, have the strongest magnetic fields in the known universe. They're nearly 100 trillion times stronger than Earth's magnetic field. And even the feeblest neutron star magnetic fields are 100 million times Earth's, and Earth's magnetic field is 100 times stronger than any steady field we can generate in a laboratory. Don't bring any metal near it. When I was in the Army, they told me, you're going to use a compass, never stand next to a tank. The metal in the tank will actually cause the needle in the compass to deflect. Give you the wrong reading. Neutron stars are extreme in temperature too. So the protons in the center of neutron stars become superconducting In other words, they're moving so fast at 100 million degrees. They're the real high temperature champs of the universe. Neutron stars are believed to form in supernovae. The stars that eventually become neutron stars are thought to start out with about 8 to 20 to 30 times the mass of our sun. Again, a different figure.
Yeah.
When the central part of the star fuses its way to iron, it can't go any further because at low pressures, iron 56 has the highest binding energy per nucleon of any element. You've seen this chart before. Let me point out iron 56. It's right up here. You can't go any further. This is binding energy. So it's at the highest point on this curve. Uranium is down here, hydrogen is down here. When you get fusion, hydrogen goes to helium. You can see the tremendous jump in binding energy. Uranium eventually will go to bismuth, okay? I don't know where lead is on this, but if uranium goes anywhere toward a higher binding energy, it loses less energy than the hydrogen loses going to helium. This is a tremendous jump from about 1 to about 7. Uranium only goes for a fraction of between 8 and 9. So fusion is much more powerful than fission. A hydrogen bomb, much more powerful than an atomic bomb. Okay? At the very high pressures involved in this collapse, it's energetically favorable to combine protons and electrons to form neutrons plus another particle called a neutrino. The neutrinos escape after scattering a bit and helping the supernova happen, and the neutrons settle down to become a neutron star, with neutron degeneracy managing to oppose gravity. Since the supernova rate is around 1 per 30 years, and because most supernovae probably make neutron stars instead of black holes, in the 10 billion year lifetime of the galaxy, there have probably been 100 million to a billion neutron stars formed. A neutrino is an elementary particle that interacts only by the weakest subatomic force and gravity. The neutron is so named because it is electrically neutral and because its rest mass is so small, hence the suffix INO. So neutral and then small, let me go back. A neutron that is very small would be called a neutrino, okay? Ino meaning small. The weak force has a very short range, and the gravitational interaction is very weak, and neutrinos thus typically pass through normal matter unimpeded and undetected, and right now they're coming right through us, the Earth, the whole planet, okay? They just go right through. Better than having them stop. Yes?
Well, if they can't be detected, then how can their existence be confirmed?
Okay, that's a very good question, and I have a very good answer. When you bombard certain particles together, you produce neutrinos. Now, how do you know the neutrino has been produced? Okay, because it affects in a bubble chamber, what's called the bubble chamber, it affects the other particles in a certain way by measuring the momentum which is the speed and the mass of these other tracks. Then you can derive from that how the neutrino came out. So without the neutrino, you can't explain where the extra energy went.
Well, it's from the conservation of energy.
Yeah,
They've also detected free neutrinos with by putting a tank in a deep cave.
yeah, in a basement or a deep cave, yeah, yeah.
Does the neutrino have mass?
Effective mass, remember, energy and mass are the same thing.
Uh-huh.
Okay, E equals mc squared, according to Einstein.
So when Paulie came up with this idea of neutrinos, he said he felt bad about postulating the existence of a particle that couldn't be.
Yeah,
But he still did it anyway.
he still did it, yeah.
And everybody's used it since then.
If we look at the structure of a neutron star, with a radius of about 6 miles, the surface gravity is about 10 to the 11 times Earth, which would be, so 10 to the 9th is a billion, right? So it's 100 billion times Earth. So 1 pound on Earth would weigh 100 billion pounds. And magnetic field about 10 to the 12th Gauss. That strong magnetic field messes up the atomic structure. So the binding energy of hydrogen rises from 13.6 electron volts to about 160 electron volts in that strong magnetic field. So the whole process of fusion is changed. And if you can still have fusion, it's possible you can get a lot more energy. In the atmosphere and upper crust, you have lots of nuclei, so it isn't primarily neutrons yet. At the top of the crust, the nuclei are mostly iron, 56, and lighter elements. Deeper down, the pressure is high enough that the equilibrium atomic weights rise, so you might find something like zirconium with an atomic number of 40 and atomic weight of 120, so there's 80 neutrons in the nucleus. At extreme densities, the electrons become degenerate, so the electrical and thermal conductivities are huge because the electrons can travel great distances before interacting. They're moving very fast.
If you've got zirconium, it would have to be at least a second generation star, because you can't produce zirconium by compression.
Yeah. Deeper yet, you reach a layer where it becomes energetically favorable for neutrons to float out of the nuclei and move freely around. So neutrons begin to drip out of the nucleus. Even further down, you mainly have free neutrons with about 5 to 10% protons and electrons. As the density increases, you find what has been dubbed the pasta-antipasta sequence. At relatively low densities, the nucleons are spread out like meatballs that are relatively far from each other. At higher densities, the nucleons merge to form spaghetti-like strands, and at even higher densities, the nucleons look like sheets, such as lasagna. Increasing the density further brings a reversal of the above sequence, where you mainly have nucleons, but the holes form, in order of increasing density, anti-lasagna, anti-spaghetti, and anti-meatballs, also called Swiss cheese. Family would have been proud.
Has anybody tried to explain electricity?
In white dwarf stars, neutrons in the atomic nuclei are very stable. Free neutrons outside a nucleus will decay to a proton, an electron, and a neutrino in about 15 minutes. So you don't find neutrons drifting around in any great density. The reason normal matter isn't comprised entirely of neutrons is the pressure of electron degeneracy. The Pauli exclusion principle states that two electrons can't occupy the same place. so they fill themselves up in orderly shells. If you compress matter very tightly, this ability to be in the same place at the same time acts as a force, preventing atom disintegration. This is electron degeneracy pressure, and it supports a white dwarf together with gas pressure against gravity. In a neutron star, gravity has overcome electron degeneracy pressure, allowing the protons and electrons to combine into neutrons. The force holding a neutron star together against gravity is the neutron degeneracy pressure. Any two neutrons, like electrons, may not be in the same state, and this neutron crowding provides a supportive force against the intense gravitational pressure. Neutrons were discovered in 1932. Very shortly thereafter, in 1934, Bethe and Zwicky proposed that neutron stars were formed in supernovae. But for many decades after that, little effort was expended on the theory or observation of neutron stars. This changed dramatically in 1967. Recall that that was the same year, the January of that year was when Oppenheimer passed away. So he never knew about this. But due to serendipity and the diligence of an Irish graduate student by the name of Jocelyn Bell and her advisor were working on radio observations of quasars, which had been discovered in 1963. Bell and some other graduate students observed periodic radio signals coming from stars labeled quasars. The discovery initiated a storm of activity that is still not abated. A number of other pulsars were discovered, eventually leading to a connection between pulsating stars and neutron stars. What happens in a pulsar star is this. The outer atmosphere of the star absorbs energy coming from the core. As it absorbs that energy, it expands. As it expands, the temperature drops. As the temperature drops, the pressure abates and the star begins to collapse. As it begins to collapse, the temperature goes back up. Okay? And more energy is absorbed and it begins to expand again. So it's constantly going through this expansion contraction. And therefore it's called a pulsating star. Because along with the compression and expansion, the amount of energy and the brightness of the star changes over time. And we can measure the period of change. By knowing the period of change, we can deduct an awful lot of information about that star. Sir?
Aren't you describing a variable star? I thought a pulsar was spinning. We were intercepting the beam coming from it.
Yeah, but it's that X-rays that we're talking about.
Yeah.
here, right?
It's energy. It's energy. So it's not only the brightness in the visible region, it's the X-rays, it's the other energy that's being produced.
Yeah, it doesn't matter. The stability of the frequency is due to its spinning,
Yeah.
not to the expansion and contraction.
No, for a pulsar it would be expansion and contraction. Yeah.
Well, the spinning causes a big flare to go up.
Well, and the spinning is related to it because you've got this huge magnetic beam sweeping into space. Yeah, so that's another factor. Yeah.
So it causes a localized intense flare to go up.
It
And
can.
that's what we see.
Yeah, it can.
It's very bright.
Okay, so Oppenheimer made a very significant contribution to understanding neutron stars, white dwarfs, neutron stars, and black holes. He is mostly remembered, of course, for the Manhattan Project, which we already spoken about, and his frequent clash with Teller was over the issue of hydrogen bomb development. Teller wanted to do the hydrogen bomb, and Oppenheimer, and rightly so, I think, figured out that there wasn't enough time to get a hydrogen bomb developed to use in the war that was going on. Remember, by this time it was like 1944.
The other point was, what was the mission of the project? To develop the A-bomb and the H-bomb? To me.
It was the A-bomb.
He was really great, so
Yeah.
he was really outside of the.
Well, you would have still had to develop the A-bomb for the H-bomb.
Yeah, right. You needed the A-bomb for the H-bomb.
They didn't know that at the time.
No, they didn't know that, yeah.
My point is, he deserved to be sidelined.
Yeah. So anyway, Oppenheimer was brought before a panel, and Teller was eventually diverted to H-bomb development. Oppenheimer lost his security clearance because of his opposition and because of Teller's testimony against him, labeling him as a threat to national security. So he was removed from the project.
I think the real crash came after the war, when Oppenheimer
Yeah,
did not
oh,
see
yeah.
any need to continue developing these terrible weapons. But Teller said, no, let's go ahead and develop a more terrible weapon. Keep up with the Russians.
I think
Keep ahead of the Russians.
No, but during the Manhattan Project.
it started during the Manhattan Project, but
He was sidelined.
Yeah.
He was just,
Yeah,
he was given his own group to work on.
yeah, yeah.
His
not
ego was
addressing
big.
They kind of diverted Teller, and then the fight continued, after the war. Yeah. By the way, I should mention, I just finished reading this book this morning. There were tremendous, normal, regular bombings in Japan. The devastation just from regular, ordinary munitions was horrendous,
Firestorm.
which I never realized. Yeah. Yeah. Yes, sir.
Yeah, Curtis LeMay did the firebombing of Tokyo,
Yeah.
basically destroyed the whole city. Anything that was not concrete was burned.
Stimson, who was the Secretary of Defense, Secretary of War, I guess it was called at that time, famously said that his biggest problem was controlling the Air Force. He couldn't stop them. They were just bombing and bombing and bombing. I mean, they had fleets of planes going over, hundreds of planes going over Japan every day.
And I think that the March of 1945 firebombing of Tokyo killed more people than both the atomic bombings.
Yeah, and the problem was too that the Japanese would build a plant, but then they would farm out a lot of the work of the plant into homes that surrounded the plant. So in order to stop the production, you not only had to bomb the plant, you had to bomb the homes. And they killed a lot of civilians.
That's what Curtis LeMay said anyway.
Yeah, yeah. So anyway, Oppenheimer lost his clearance, lost his position with the Atomic Energy Commission. In summary then, he co-authored 3 papers in the 1930s that had a very significant impact on further research into neutron stars and black holes. His obsession with neutrons was fully displayed in his management of the Manhattan Project. Because as I said, and this is my own opinion, I didn't find this written up anywhere, but from reading this book and other papers, it was the initiation, production, and control of neutrons to sustain a chain reaction that were the main focus of the Manhattan Project. Because they didn't want premature explosions, they didn't want explosions that weren't fully efficient, and in order to get that, they had to manage the density, production, control, and inclusion or containment of neutrons. Like Einstein, Oppenheimer became a pacifist after his effective management of the Manhattan Project. He was managing a project that had, at its height, I estimate, and this book confirms, about 300,000 people. Under his direct control, he had 3,000 people. But at Oak Ridge alone, there was something like 85,000 employees. Then there was Hanford, and there was Los Alamos, and there were labs in Chicago and all over the country.
Was he in charge of those other ones? I think he just had Los Alamos.
Well, his main focus was Los Alamos, but he had to bring everything together. And Groves was
General Groves.
ostensibly in charge of the whole thing, but Groves didn't have the technical knowledge. And as Stuart pointed out, Oppenheimer was widely respected.
Well, Hans Bethe, who headed the theory section of the Manhattan Project, during his quantum mechanics class, said that when Oppenheimer died, the greatest American physicist just died.
Yeah, when Oppenheimer died,
And coming from Bethe, that really meant something.
yeah, this famous physicist Bethe said when Oppenheimer died, the greatest physicist that ever lived
In America.
in America had
American
died.
physicist.
Yeah. He didn't want to insult Fermi
Well,
or Einstein.
Wasn't Leslie Groves more like a general manager of
Yeah,
an organization?
He was a money man, yeah. But he started out as a colonel, and then he went to his boss and he said, you know, they're not going to pay attention to a colonel. I have to be a general. So they kept promoting him. I think he got up to lieutenant general.
Groves built the Pentagon. Right before the Manhattan
Yeah,
Project.
that
That's
was
why he got
his
the job.
major achievement before the
That was a
Manhattan
pretty
Project.
great job.
Yeah. He was an engineer, yeah,
Well,
an engineer.
he managed.
Yeah. Like Einstein, so Oppenheimer famously said after the Trinity test at Los Alamos, where the first atomic bomb explosion occurred, now I am become death, the destroyer of worlds. So I think he probably began to realize the tremendous energy that could be released by an atomic explosion after he had finally built the bomb. As a star dies, it may become a white dwarf sustained by electron degeneracy. Larger masses will compress further to a neutron star sustained by neutron degeneracy, and very large masses will compress further and become black holes. So, somewhere in space right now, there are two hydrogen molecules, well, two hydrogen atoms, two protons, or a proton and an electron form a hydrogen atom. Two of these atoms are floating around and they are getting close enough to each other so that the gravitational attraction between them is great enough to bring them together. Now you have twice the mass, and another hydrogen atom is going to be floating by and it'll be captured. Now you have 3 times the mass, another one comes by and is captured. 2 more come by, and the more that are captured, the faster the rate of capture goes up. A star is being built somewhere, and just how many hydrogen atoms are pulled together in a short period of time before fusion begins, before the gravitational pressure is great enough to raise the temperature to the point where these atoms are moving fast enough to fuse, okay, determines what kind of a star you're going to have, how much mass you're going to have. And that determines the fate of the star in its future life. Kind of an amazing thing. Any questions?
Any more questions now?
Yes. Has anybody come up with the idea of what is electricity?
Flow of electrons.
It's flow of electrons.
You mean, what is
Electrons
a,
don't
you
flow.
mean, you're really asking, what is an electrical charge?
No, what is electricity? When you push a switch and you got a light bulb at the end of a wire, and
It's the flow of electrons.
but electrons don't flow, we know that.
Yes, they do.
Oh, yeah,
You
oh,
put a
yeah.
battery on a wire and you'll get flow of electrons.
Yeah, you can measure the flow of electrons with an
You
ammeter.
have an instrument that it's called an ammeter,
Right,
but you don't know electrons are flowing. You don't know that at all.
well, I think you do, I think you
You've
do.
got a copper wire.
Okay, I think you do. I think,
What you're saying is electrons are flowing through that copper wire?
No, you have to have a potential
Have you
difference.
ever
You
seen
have
a
to have
virus when
battery
you
or
get sick?
Yeah, three people talking at the same time.
It may not be the same
You
electron.
got a difference of potential, that I understand, but the flow of electrons, when you've got a
Three degrees of engineering, I wasn't there.
when you got a copper wire, and you have electricity flowing through that copper wire, and you shut the electricity off, you still have the copper wire, and you still have the electrons in that copper.
That's right, they're free electrons, that's why they flow, they're free electrons in a copper wire. And when you get like a potential difference between the ends of the wire, you get some electrons coming in the wire at one end and going out the other end, and there's a little bit of drift in there, but it's not like water, you know. Have you ever seen this long tube with ping pong balls in it? You put a ping pong ball in one end and another.
see me after class. Any other questions? Yeah, yeah. Any other questions? Yes, Jane.
What did he do after he retired, or did he retire?
He went back to Berkeley and,
Well, he became the head of Princeton.
he wrote and he formed this institute and lectured on physics, you know, which is typical of, you know, a lot of the sciences that we've talked about. Became a writer, and still was a pacifist. Yeah. But kind of faded, you know, didn't do any more research.
Kind of like his star.
Yeah, yeah.
Did he start a peace group?
He started a group for arts and science. Yeah. Is there a question back here? Yeah.
It's not a question, a comment. I used to worry about the sun burning out in a few billion years. Now I'm worried about the Teller's H-bomb, which is to get us in our lifetime.
I think it's a race between global warming and nuclear extinction. And now the Amazon rainforest is burning. That's only going to increase the rate of global warming, I think.
I think Arthur Clarke said something very profound when he said that the survival value of human intelligence has not yet been demonstrated.
Very good, yeah.
I can say another thing about Oppenheimer is that before the war, he apparently was involved in investigating photosynthesis and various biological reactions.
Oh, really?
Because it was being done by nuclear physics experiments. Use cyclotrons and bombard
Yeah, interesting.
molecules. But I thought it was quite interesting that that kind of background would then switch to bomb making.
Yeah, yeah.
Yeah, Einstein said the war after the next war will be fought with sticks and stones.
Thank you very much. Have a great week. See you next week.